Good morning, good afternoon, good evening, everybody. I'm Gennady Andrienko, and it is my pleasure to chair this session on urban spaces. We have 6 excellent papers to be presented, and we start with the first one, Towards Better Bus Networks, a Visual Analytics Approach.
Hi everyone, I'm Dee from Zhejiang University. Today I will present the latest paper from our group, Towards Better Bus Network, a Visual Analytics Approach. In the last few centuries, bus networks have become one of the most widely deployed public transit systems. As the city evolves, bus networks are typically updated every 3 to 5 years to match the travel demand. Traditionally, bus routes are planned manually with GIS software, which is not very efficient. The advance of data sensing technologies facilitates many data-driven approaches. However, the generated results are often limited and difficult to optimize. In recent studies, Pareto-optimal route generation was proposed to make the planning procedures more interpretable and flexible. Instead of iteratively guessing the best routes with the given parameters, the Pareto-optimal model accepts a list of performance criteria that can be measured for each route, such as service cost and demand satisfaction. The model then searches for feasible solutions and generates a set of routes, where none of them is strictly worse than any other. Therefore, the experts can evaluate this set to make informed trade-offs among the criteria. However, improving bus networks remains a difficult task. For one thing, it's hard to analyze the huge and complex bus network to determine which route should be improved. For another, urban planners have to evaluate a large solution space to find the best replacement routes. To tackle this problem, we propose a bus network visual analytics system. The system helps users first analyze the performance of a bus network and identify problematic routes based on trip and transfer records. Then, the alternative routes to a selected route can be obtained in real time with a Pareto-optimal route generation model. Finally, users can evaluate these alternative routes based on their spatial and numeric characteristics and decide which one is the best. Developing such a visual analytics system presents 3 challenges. The first challenge is to perform the in-depth analysis of complex route networks. A large route network may comprise thousands of bus routes, generating millions of trip records every day. Such a complex dataset will require a scalable and effective analysis approach. The second challenge lies in the generation of the replacement routes. In real-world scenarios, generating the routes involve many constraints, such as stopping the routes at a location. The route generation model must be extended to support these constraints. Moreover, the model is progressive because it's often impossible to exhaust the solution space. Therefore, the experts should know when they can stop the generation. The third challenge is to evaluate a big set of alternative bus routes. The system should help experts to efficiently decide which route is the best from the diverse alternatives. To address these challenges, we collaborate with domain experts and develop a 3-stage workflow, including the exploration, manipulation, and evaluation stages. At the exploration stage, a spatial overview of the bus network is required to show the distribution of the routes and guide users to locate ineffective parts of the network. Moreover, the movement of passengers inside or between the routes can provide key insights to identify the problematic routes. We designed 3 levels of analysis to support these requirements. For the network level, a map view is designed to provide a spatial overview of the entire network. For the route level, a ranking view is integrated to show the performance of the routes. For the station level, a matrix view is proposed to visualize the passenger flows and transfers among the stations in a selected route. The map view provided by the network level analysis comprises the route and the aggregation layers. The route layer draws all bus routes in blue with opacity, and the aggregation layer shows the aggregate statistics of transportation zones with a no-link diagram. The transportation zones are obtained by clustering bus stops based on the distance. Moreover, a zone glyph is placed at the center of each zone to summarize its key statistics. Around the glyph, a divergent passenger flow distribution shows the amount and directions of passengers leaving from and arriving in this zone, while inside the glyph, a radar chart is used to visualize 6 criteria that measure the performance of route segments inside the zone. Additionally, the thickness of the links indicates the number of routes connecting the zones. The route level analysis integrates a table-based ranking visualization for the routes. The visualization allows the users to flexibly filter and rank the routes based on the criteria to find interesting routes for further analysis. Selecting a route in a ranking view brings the users to a matrix-based visualization that summarizes the trip records. The opacity of each cell encodes the number of passengers. The cumulative passenger flows are shown in the bar charts. To visualize the temporal distributions of tap-on and off records, 2 horizon charts are embedded to show the records aggregated by day, hour, or weekday. The numbers next to the station labels indicate the numbers of the transfer routes, while the opacity of the circle encodes the number of the transferred passengers. Clicking on a circle opens a list of transferred routes. The pie charts before each route shows its contribution to the transfers. The users can further examine the transferred routes in a linked matrix. Finally, we rotate the view to better accommodate multiple matrices. After a problematic route has been determined, the experts move on to the manipulation stage to generate alternative routes. They also need to monitor the progressive generation processes to find out when the results are good enough. For the generation of alternative routes, we improve the model's computational efficiency and extend it with new constraints. For the inspection of the result quantity, we enhance the model's interactivity and design a manipulation interface to allow the users to monitor and control the route generation. The evaluation stage aims to help the expert determine which alternative route is the best in terms of topology and criteria. Although the model greatly reduces the size of the solution space, the experts still need to evaluate hundreds of the routes. To facilitate efficient decision-making, we propose a progressive strategy. Instead of presenting every alternative route, the system first aggregates similar routes into route groups. The different paths in each group is called conflicts. Then, the system allows users to iteratively compare and select route groups to resolve the conflicts, and the best routes can be obtained eventually. We develop a route clustering algorithm to aggregate the routes. Initially, we consider each route as a route group. The combinations of the groups are enumerated to decide which aggregation will result in the groups with the most shared stop and the minimum variance of the criteria. The clustering process is repeated until the number of the route groups is below the threshold. The conflicts between the final route groups can be identified with the longest common sequence algorithm. To resolve these conflicts interactively, the ranking table is divided into multiple groups corresponding to the conflicts. Each row in the group represents a route group that resolves the conflict. If a root group comprises multiple roots, its criteria are visualized with box plots. Otherwise, we use normal bars to indicate that this will be a final choice. The topology of the conflicts are also visualized on the map with a node-link diagram. Different markers indicate the conflict status of the stops. Therefore, the users can interact with the ranking table and the map to progressively evaluate the routes and determine the best candidate. To evaluate the effectiveness of our approach, we present two usage scenarios on real-world bus network data collected in Beijing during 2013. For the first usage scenario, we identified an abnormal transportation zone and several deficient route patterns with the exploration interface. For the second usage scenario, we show how to interactively obtain the best replacement for a problematic route. After the exploration stage, we decided to optimize the route by rerouting it to a nearby place of interest and a hospital. We started the route generation by anchoring these two locations. 132 alternative routes were obtained, resulting in 2 conflicts and 4 route clusters in a ranking view. The third cluster had the largest passenger flows but the lowest route directness because the routes satisfy the anchoring constraints by taking 2 detours. The first and the second clusters shared a similar performance in terms of criteria, but the routes in the first cluster would stop at the east gate of the temple, potentially attracting more passenger flows. Therefore, the first cluster was selected. After the selection, another 2 conflicts with 3 clusters turned up in the ranking view. The third cluster had the most passenger flows because the routes were connected with a metro station. Hence, we proceeded with this cluster. As the decision-making process continued, we obtained 1 conflict with 2 clusters. The difference between these 2 clusters is that the first stops at a bridge and the second stops at a residential area. Therefore, the second cluster was selected because it was more promising. Finally, only 5 routes remain in the view, categorized into 3 clusters. While the third cluster has the most passenger flows, we found that the flows were obtained by taking many detours, which might greatly impact the bus rider's experience. For the second route, 2 stops were too close to each other. Therefore, we came to a conclusion that the first route might be the best alternative. In summary, our contributions include characterizing user requirements, extending the route generation model, developing and evaluating a novel bus network vision analytics system. In the future, we plan to implement more constraints and incorporate additional datasets. The scope of our study can also be extended by integrating scheduling, timetabling, and resource management functionalities. We would like to thank the funding agencies for their generous support. That concludes my presentation. I'm ready to take questions. Thank you.
Thank you very much for your presentation. It is very, very interesting, and I see that you deal with really complex and challenging and extremely important problem. I wonder if you take into account the frequency of routes. You may have one bus in 5 minutes, in 3 minutes, or one in an hour. I didn't notice anything about that in your presentation.
So currently in our system, we only consider the spatial constraints of bus routes, but it would be great to incorporate additional functionalities like timetabling, resource management. In our future work, we will consider incorporating these functionalities. But for now, our scopes mainly covers the spatial planning of bus routes.
I see. Well, I had a follow-up question if you take into account with temporal variation of passenger flows, but I understand that you work only with space. But if you go deeper into the space domain, I also have a question. In one of your scenarios, you noticed that a bridge over a river has a special meaning and introduces some impact on bus efficiency. Maybe it would make sense to compute a variety of geographically related criteria values like presence of bridges, presence of tunnels, whatever, maybe left turns on intersections that are especially challenging and buses may have to wait. So consider if you can add such criteria to your optimization engine.
Yeah, it would be great to incorporate these functionalities. For the first question, we did consider incorporating like temporal variation in passenger flows. Like in the first exploration interface, users can check the passenger flows and their temporal distributions. So in fact, they can incorporate these factors into their consideration, so they can detect whether the bus routes are functioning properly. So yeah, I think that would answer the first question. So for the second one, actually I didn't follow. Could you please?
Okay, I think we will continue discussion offline because we need to move on to the second presentation. Thank you very much for your presentation and answering questions. So we moved ahead to the second paper, Topology Density Map for Urban Data Visualization and Analysis.
Hello everyone, I'm Zezheng Feng from Hong Kong University of Science and Technology. Today, I will introduce our work, Topology Density Map for Urban Data Visualization and Analysis. This is a joint research. I will thank my co-author, Haotian Li, Dr. Wei Zeng, and my two supervisors, Prof. Shuang-Hua Yang and Prof. Huamin Qu, and they are really awesome. This is the agenda for today's presentation. Road network is an important infrastructure in cities. With expansion of cities and evolution of transportation technology, road networks are becoming increasingly intensive and unobstacled. Consequently, two geographically distant locations may have a short commuting time due to road connectivity. Like these two bridges, which connect two sides of the river together. Hence, road network is of importance in many real-world applications, including urban planning and urban scaling analysis. Density map, as an effective visualization technique, is widely used in urban analysis, which involves spatial distribution patterns. A density map depicts the continuous distribution of scalar field in a 2D planar space by assigning a unique color to each individual scalar value. It is widely used in movement visualization, in urban analysis, and urban planning. Kernel density estimation is a common non-parametric model which typically applies a kernel to the proximity between two locations. Combining with the real cases, we discuss our motivation in three aspects. The first one is topological. Locations in urban area are connected through roads and intersections. If we want to go from A to B in the figure at right, we have to go along the road rather direct from A to B. In most cities, a road has two different directions and like Euclidean distance. The proximity from 2 points could be very different from that the other direction. If the road from C to B is under repaired in the picture, we can go from B to C and then to A, but we cannot go through A to C to B. And the third one is the access time between locations depends much on traffic conditions. that vary over time, and the peak time off-peak time may be different.
According to the two mainstream methods, KDE and network KDE, we concluded the requirement of topology density map. The first one is correctness. Our method takes dynamic traffic condition and topology of road network into consideration. The second is intuitiveness. As the figure shows, network KDE can only measure the density propagation along road network that provides 1D measurements and lack the density fields over a 2D space. However, most human activities take place at locations not covered by road networks in a city. The visualization is unintuitive, making urban analysis less effective.
So, in this work, we define the access time between a source point of interest and the target location, and using scalar fields distributed over space to represent it.
Next, we will introduce the key steps on how to construct a topology density map. The inputs include point of interest H1 and H2, and the road network G with vertices A, B, C, and D. The goal is to estimate the density field for arbitrary point P within polygon A, B, C, D. We first estimate the density propagation along the road network from point of interest. We constructed a directed Xiatian graph for each point of interest to facilitate the accessibility propagation estimation. Each directed Xiatian graph starts from the corresponding point of interest and connects all intersections by directional road segments, and the age direction indicates the travel direction of the corresponding road segments.
Given a directed Xiatian graph, we can easily find the shortest path from a point of interest to all vertices using the Dijkstra algorithm. All edges here are weighted according to the access time retrieved from traffic data. For each vertex, we select the point of interest with the least access time as the most accessible point of interest. We can then compute the density propagation along the road network. Here, we use the color of the most accessible point of interest to encode an intersection. That is, A and B are color blue, while C and D are color green. Moreover, to better depict the density propagation process on the road network, we further encode road segments with tapered lines that are preferred for graph readability. Next, we extend the density estimation from a 1D road network to a 2D planar surface to fulfill the intuitiveness requirement. Here, we illustrate the process with density estimation for an arbitrary point P as in the figure. Then we compare the density. We associate an arbitrary point P to road network by connecting P to the neighboring intersections, yielding straight walkways AP, BP, CP, and DP. Given that we have found the most accessible point of interest for each intersection, we can compute the access time from P to each point of interest by summarizing the network proximity of each road segment and the utility distance of the straight connection and find the best one. Hence, we can estimate a density field for P with respect to H2 as the equation. An example of the generated topology density map is presented in the figure.
We conduct two case studies. We select the Haotian district in Shenzhen as the study area. We first verify whether the topology density map can present the density fields accurately with requirement R1 by taking both road topology and traffic condition into consideration. In the selected area, we find that there are two different points of interest, H1 and H2. To explore it, we generate a new density map by removing passes FE and ED. We can find that removing passes makes path FED inaccessible, yielding changes to road topology. Therefore, previous path H2 FED with the shortest access time is no longer available. This affects the construction of the topology density map in terms of estimating the density propagation from point of interest and determining the source point of interest. Hence, the resulting topology density map can also reflect the changes. In contrast, Euclidean distances between arbitrary locations in the regions and point of interest are unaffected by road topology change, resulting in unchanged planar KDE. Then, we choose another area. This area is affected by H3 and H4. To explore the influence of traffic conditions on density fields, we reduce the average speed of road segments Mn and No manually, which simulated peak hours and non-peak hours. The density field changes correspondingly. However, it changes from H4 to H3 in region 5, and the density field decreases as well, caused by lower speeds of road segments Mn and No. This phenomenon indicates that although the Euclidean distances between intersections remain unchanged, dynamic traffic conditions can lead to variations in shortest paths on a road network and ultimately alter the density distribution on a 2D planar surface.
Next, we demonstrate the intuitiveness of topology density map in presenting density distribution, which is a requirement R2, which facilitates the process of finding the optimal location of a new public service facility. Here, we use hospitals in Futian district as a point of interest. Figure presents density field of accessibility measured from the hospitals, which is unbalanced in the district as currently the hospitals are concentrated in the east part of Futian district. The government decided to build a new hospital and tries to find suitable location for a hospital. A critical consideration here is that hospitals should make the distribution medical service more balanced. In other words, to maximize the increase of hospital accessibility for the whole district, two possible locations for the hospital location are available. We can put the new hospital in the region where density is low. Another place is the hospital in the region where the density is already high. These two subfigures shows the effect that after we adding two different hospitals respectively. For this part, it is obvious that the density field in the southwest part increases. This intuitively depicts how much the region can benefit from a new public service facility. Moreover, because the density first propagates along the road network, and then propagates to a 2D planar surface, the change in density distribution on the road segment is obvious. In contrast, building a new hospital in this region worsens the unbalanced distribution of medical service. The study clearly demonstrates that the topology density map generates intuitive visualizations that can facilitate problem identification and decision making.
Table 1 shows the running time between our method and KDE. Our topology density map takes pre-computed directed stellar graphs, starting from each point of interest to all intersections using Dijkstra's shortest path algorithm as additional input. We can conclude that the computation efficiency for our planar KDE is affected by both image size and number of points of interest. The computation efficiency for topology density map is affected by image size. The computation efficiency for topology density map is also affected by the number of intersections rather than the number of points of interest.
And this is the limitation and future work for our research.
And we also provide some take-home messages. And noted that after combining different data sets, our method can be used to analyze other urban problems related to the movement patterns, such as the economics in the urban area or the mobility pattern for human beings.
Okay, thank you very much for your presentation. While we are waiting for questions in Discord, I have a couple of questions myself. First of all, I like very much how you do with density map and how you show distribution of travel time over geography. But what I'm missing in your map is the distribution of population. Is it possible somehow to combine? It may happen that there are empty spaces, non-residential areas or agriculture, and they don't need much access to the hospitals at all. Is it possible to modify your method so that you can take into account the human distribution of humans?
Oh yes, actually, our work is focused on how to draw a new approach to draw density map. And we also mentioned that in the future work, if we add some other data sets like the population distribution or some like the metro lines, and it can be used to some I think some useful systems like traffic monitoring system, and yes.
Yeah, thank you. And another possible direction of future work might be to take into account the time variation of accessibility times, because it may take longer time at busy hours and much quicker on Sunday or overnight. And it would be interesting to look at variation of times, travel times, and the impact on changes of accessibility zones.
Yes, thank you.
Okay, thank you very much. And we have to go ahead to the next paper, which is UrbanMotion, Visual Analysis of Metropolitan-Scale Sparse Trajectories.
Good day, everyone. I'm Lei Shi from Beihang University, presenting UrbanMotion, a visual analytic system for very large sparse trajectories. This is joint work with my students and colleagues in Beihang, Chinese Academy of Science, Yahoo, Zhejiang University, and Talking Data Incorporation. We first introduce the background research problem on this work. The study of human trajectories has been an interdisciplinary area joining many fields, including visualization, to model human behavior and to analyze and present them. With the trigger of big data and wide adoption of GPS and mobile internet, the opportunity becomes available. 10 years ago, the group of Balabasi analyzed 100,000 mobile users, and here are trajectory of 40 users in their data. About a couple years before, we are able to touch 40 million of human trajectory in densely populated megacity in China. The Metropolitan-Scale trajectory visualization could be an enabled feature for many applications, such as traffic optimization, city emergency management, and business site configuration. Our trajectory data is collected by Talking Data Incorporation, an analytics platform to synthesize data from many mobile apps. These apps are installed on billions of devices in China. In some cities, the data covers more than half the population. While most Paris trajectory data are one application only, for example, taxi data on major roads, or phone call data upon calling, our data is more uniform on space and time due to the synergy from multiple apps. In this work, we studied 3 months datasets from 4 central Chinese cities under strict Paris agreements. To understand the new opportunities with this data, we set up interviews with 3 domain experts: an urban planner, a public safety officer, and a business analyst. Details can be found in the appendix. 4 key user tasks are summarized in visualizing the new trajectory data. T1, overview of global population movement. T2, examine local movement patterns, for example, hotspots, hubs. T3, analyze the correlation of population movement and their underlying distribution for important urban issues, for example, work-life balance. T4, detection and visualization of anomalies from temporal dynamics of urban movements. Accomplishing this task is not straightforward. Major challenge came from the side effect of big trajectory data. Unlike previous data, our data from mobile apps are not uniformly measured over time because of the power and privacy constraints, as shown in the top left figure. Location records are obtained in a birthday usage period, followed by long silence. We call this characteristic the long-tailed sparsity. How to extract movement records from such trajectory data, and how to abstract them for population movement visualization. Classical aggregation methods use a granularity that will fold mostly tragic local movements in the same cell, and the visualization will be incomplete. Related work. In the literature, a lot has been done. In aggregating movement data for visualization, the trajectory-oriented aggregation is more relevant to our work. Approaches like mobility graph require accurate origin-destination info on each trajectory, generally OD flows for visualization. This is only available from sparse trajectory. Meanwhile, existing visual representation of massive movements are also not designed for sparse trajectories. There are indeed a few works on sparse social media trajectory visualization and sparse vector field visualization, but none of them is based on the long-tail sparse trajectory data as ours. Over existing work, we propose a pipeline design in the UrbanMotion system to fulfill the design goal of this work. We will introduce the stage of the pipeline in details. First, the trajectory analysis stage. To extract movement records from sparse trajectory data, we first define the concept of stay and travel trips in the trajectory. The definition is consistent with existing literature. Thanks to the long-tail sparse nature of our data, we are able to design an algorithm called SDS to accurately infer the stay travel trips on each trajectory. Again, you can find the details of the definition and our algorithm in the paper. On the dataset for Beijing, the algorithm detects close to 1% records as travelers and half records as stays. Others are undetermined. Though the percentage of travel is low, considering the huge size of the entire data, that is 8 billion, it is still capable to represent the population movement in the city. After travel trip extraction, millions of local movement vectors need to be abstracted for visualization. We adopt a fundamental strategy in spatial data analysis, grading. Vectors are partitioned into spatial temporal cells. Movement in each time slot is visualized separately, and movement vectors in each spatial cell are aggregated together. On aggregation methods, we first introduce a classing approach to reveal global movement patterns. As shown in the bottom right figure, each vector in a cell is represented by a point in the boundary of the cell circle. DB scan is used to detect the vector cluster from these points. To reduce the computational complexity, we design a 1D DB scan, which has linear complexity by the number of vectors. In another aggregation method, each vector is map-matched to a road to better reveal local movement patterns. We apply an algorithm by Wegler. The algorithm computes the matching score between each movement vector and its road segment candidates. The segment with the highest matching score is selected. Both location and directionality property are considered in the matching. The map-match vectors grouped by road segments. The final output format is the same with the movement classing approach. There are clear differences in the two aggregation methods. See the left figure. Classing leads to fewer but larger movement flows and a more abstract view. It is because movements in similar directions but not in the same node can be clustered and displayed together. On the other hand, the map-matching result in the right figure displays movements in every single road segment and is more effective in discovering detailed movement patterns, for example, road utilization. After movement aggregation, we further explicitly detect local and global movement patterns for highlights in the visualization. Spatially, we discover half cells and channel cells by a bimodality coefficient metric. Temporally, we detect possible anomalies from the dynamics movement in each cell over time. Hourly, daily, weekly anomalies are detected. As shown in the bottom right figure, on the day of marathon game, the movements along the game trail become significantly lower than the same hours in normal days. Visualization. We studied the possibility to apply wind map, that is the bottom left figure, to display population movements in cities, that is the bottom right figure. Both wind and population move in groups of particles in the first trajectories. Both are processed into a vector field for visualization. However, population movements could have multiple directions from the same location. People generally move along road networks, and also their movement correlates with population distributions. In urban wind map, we propose several techniques to adapt to this difference in design. First, the animated flow visualization design is used, which applies multivariate visual encodings. Flow thickness represents movement volumes. Color saturation or lightness represents movement speed. Animation is used for flow direction. Two color themes can be selected for different scenarios. Second, we apply pattern-based flow seeding over original random seeding wind map. Both high-volume flows, hubs, channels detecting the analysis can be selected as seeds. In case a hub is selected, all flows from the hub are traced independently. This enables visualization of multi-directional flows. To trace each seed flow, a deterministic trajectography algorithm is applied. The algorithm provides several parameters to control the continuation and termination condition for flows. Third, we propose multi-layer map design. Beneath movement flow visualization, several heat maps can be displayed to show the distribution population. We include movement OD map, speed map, population density map, and anomaly map for event detection. Case studies. We apply UrbanMotion to study the commuting pattern in Beijing. In a typical weekday, the population movement in the morning period is visualized, as shown in the bottom left figure. There are several hotspot regions with large commuting flow. Notably, the Xiatian and Huilongguan region in the north has much dimmer flows, indicating lower speed and computing. We zoom into the region to analyze local movement patterns. The OD heat map on the bottom middle tells us during the commuting, people are moving from their home at Huilongguan, the blue hotspot, to work location in Xiati, the red hotspot. No such biotite pattern is found in the noon after commute time. They can also be observed that Xiatian and Huilongguan regions are cut by G6, a major road of Beijing. There are only a few streets crossing G6 and connecting the two regions. The visual analysis demonstrates the key bottleneck of road network design for local transportation. In another case, the system is used to monitor the traffic status in Beijing. On the morning of a weekday, some anomalous patterns are found. The color of most movement flows is much brighter than usual. This indicates a higher commuting speed. Also, fewer movements are found in the local regions. This event is quickly linked to the rainstorm started earlier on that day, which has a large amount of precipitation for Beijing in the recent decade. It is reported that the subway system of the city have a record high number of passengers. We infer that most people previously commuting by bus, bike, or other ground vehicle have switched to the subway system. This explains the pattern of a higher commuting speed and less local movement. Commercial site configuration in Binhai New Area of Tianjin, another big city in China. In 8 a.m. of a typical weekday, major movements heights for the industrial park as shown by the red hotspot in the bottom left figure. People commute here for work. By the noon of the day, that is 12 a.m., as shown in the bottom middle figure, the top destinations switch to the areas beside Hai River, where many commercial centers locate. The Binhai New Area is a famous site of tourism. Deploying business or commercial branches along the Hai River can be advantageous, and the time for sale can be scheduled to noon. Proceeding to 6 p.m. in the afternoon, as shown in the bottom right figure, we can see that 3 movement hubs co-located with key railway and bus stations. Movement traffic there is several times higher than surroundings in the afternoon. People are heading home, and tourists are going out of town from the stations. Placing billboards around this station can draw the attention of diversified population. Conclusion. This work proposes a system to visually analyze population movements in cities from billions of mobile location records. Our key contributions are visual analytic techniques to deal with long-tail sparse trajectories. First, the movement extraction method, including a formal definition of travel trips and an accurate yet efficient algorithm to extract travel records. Second, the movement aggregation methods, including a fast movement vector classing algorithm and the application of map matching algorithms. Third, the movement visualization design with improved flow generation algorithm and the wind map metaphor adapted to the characteristics of population movements. That's all. Thanks.
Hello, thank you very much for your presentation. Your system looks really beautiful, and I enjoyed watching your video. There are a couple of questions, and first of all, you mentioned in the beginning that the key part of your approach is map matching, and you are very proud that map matching improves the visual quality of the aggregates. But you also mentioned that sometimes at bad weather, people change from bicycles to metro lines. Both bicycles and metro lines don't really follow the street network. They have their own networks. So how don't you see there is a contradiction here?
Yeah, actually, it's a very good question. Thank you for the comments on our paper. So your question is for the bicycle movement, it do not strictly follow the street map, right?
Yes.
Yeah.
And metro trains as well.
But I believe for the case of Beijing, even we ride a bicycle, we follow a small street. If you look at the map we show for the map pattern result, it's very detailed. And actually it covers all the, not the major roads, but also all the streets. I cannot actually imagine how we ride a bicycle without in a small street. Actually, every street is mapped in the Beijing roadmap. And it do not only include the major roads like G6, but also include many very small streets like Hutong in Beijing. It is also covered by the very detailed map. So I think the map matching paradigm or algorithm we use can cover this maybe bike riding, but maybe for working, maybe they do not strictly follow the roadmap. But the question whether we want to capture this more movement in this metropolitan scale movement realization, maybe we only want to look at the aggregations, and more detailedly we want to look at the bike riding or small slow movements, but not the working. Because working by our definition sometimes is not classified into a travel because we're moving very slow. It may not be a moving. It depends on the definition and depends on the threshold to classify the travel and the stay. So
I see. Thank you very much. I'm afraid we have to go ahead with the next presentation. Again, thank you very much. And we continue with the third paper from this, the fourth paper from this session, revisiting the modifiable area unit problem in deep traffic prediction with visual analytics.
Hello, welcome to the talk revisiting the modifiable area unit problem in deep traffic prediction with visual analytics. This is Zheng Wei from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. And this is our collaborating work with researchers from Huamin University, Central South University, University of Warwick, and Zhejiang University. So we know traffic prediction is very important for urban planning and traffic management. Okay. Existing algorithms such as ARIMA takes advantage of repeating occurrence in temporal historical data. For instance, this is a spatial and temporal view of the traffic movement in Shenzhen. We can see like the area of airport and the south part of Shenzhen. We have more traffic movement, and we can also see peak and non-peak hours in both weekdays and weekends. And these temporal patterns are repeating every week. Okay. Nowadays, more and more deep neural networks are applied in traffic prediction, such as to capture the complex nonlinear and spatial and temporal properties. So we investigate ST-ResNet that predicts the inflow and outflow volumes in regions. Okay. Here is how ST-ResNet works. So first, it will partition our underlying territory into grids. And then it will aggregate the inflow and outflow in each grid. Next, it will model the spatial temporal flows as a sequence of raster image. And then it will apply the convolution-based residual neural network to make predictions. However, we know the traffic aggregation are influenced by both partition shape and the scales. For instance, in this movement data, the aggregation can be aggregated by different grids or by traffic analysis zones. And we can also aggregate in different scales, for instance, the 2x2 grids or 4x4 grids. This phenomenon is called the modifiable area unit problem. Okay. It can be regarded as an example of Simpson's paradox. Okay. Also, this kind of inputs can be small difference, but the output can be significantly different because of the adversary interpretation problem of DNN. In collaboration with a researcher in geography and transportation analysis, we distill 3 research goals. First, we would like to understand the MAUP effect on traffic aggregations. Second, we would like to understand how the output, the prediction, will vary upon the input. And third, we would like to support the exploration of an individual region instead of some kind of summary statistics like root mean square error. Okay, we further derive 3 analytical tasks. First, we would like to support spatial variation exploration of both input traffic and output predictions. Second, we would like to support spatial association analysis to examine the spatial dependency and the spatial non-stationarity. And last, we would like to support scale-independent comparison such that to remove the scaling effect of different attribution ranges. For instance, here we have 2 predictions, and both of them the mean absolute error is 10, but we prefer the first one. One thing to mention is that the internal working mechanism of DNN is not our interest because we are not model developers. So the MAUP is very important, and the visualization community has developed many spatial partition algorithms to support better movement visualization. And also, we have developed many visualization and visual analytical techniques to explore and suppress the MAUP. Of course, the GIS community, they have formulated many theories for reasoning the MAUP, developed many techniques to quantify the MAUP, and identified the impacts of the MAUP on different applications. Recently, there was a paper suggests that visualization techniques are strongly encouraged to explore the MAUP. However, they also pointed out that existing visualizations are limited to the newness of the techniques and the complexity of displaying such a large and diverse amount of spatially represented data. Okay, so they developed an ESDA approach. So we checked what kind of visualization techniques they developed, and we found that they mainly use a bivariate color place map and a Morris I scatter plot. To the domain experts, these visualization techniques are more easily understandable. Okay, and both of them can actually be categorized as unity visualization based on the design rationales of coordinated views, overview plus detail, unity visualization. We develop a coordinated multiple view system that mainly includes a control panel, a bivariate map, a scatter plot, and a multi-scale attribution view. The visualization modules mainly include, first, a bivariate map to support spatial variation exploration, task 1. So the map can show traffic volume and the prediction errors simultaneously using value suppressing uncertainty palettes. So here we would like to emphasize those grids with higher prediction errors, that is the grids in dark red. We also integrate a temporal view to show the temporal variations of all time steps of a selected region. Second, we include a Morris I scatter plot to reveal the spatial autocorrelation of traffic volumes in each grid-based partition and the local tract task 2. So here we use queen continuity spatial weight matrices with 3 times 3 matrix size, that is the convolution kernel size used by spatial ST ResNet. We also decompose the global Morris I into local indicators of spatial association indices. Okay. Last, we design a multi-scale attribution view to support scale-independent comparison, task 3. So here, each dot represents a region with the position sorted in ascending order by absolute prediction error, the size corresponding to the traffic volume, and the color encodes according to scale-independent matrices. We also design the 3 plots of partition scales in a hierarchical structure to support comparison. Our alternative design for the multi-scale attribution view is the nonlinear dot plots. In nonlinear dot plots, the horizontal positions are based on prediction errors, and the dot size are adjusted based on the number of dots in each stack, colored based on scale-independent matrices. However, we can see many gaps in between stacks, so the space usage is not very efficient, and the size doesn't corresponding to the traffic volume, so it can lead to misleading correlation analysis and spoil multi-scale comparison, because the real dot size should be like this. We evaluate our system using 2 months taxi data in Shenzhen. We partition the Shenzhen area using grids partition and also TAZ partition followed by rasterization, and partition the region into 3 scales of 50 times 25, 100 times 50, and 200 times 100. That is, we totally build 6 ST ResNet models. So in the first study, we would like to diagnose multi-scale predictions. So in using the root mean square error, we can see that grid partition achieves the best performance at scale 100 times 50. However, if we compare using the scale-independent matrices, we can see actually the scale 50 times 25 is best. Okay. Second, if we compare root mean square error at a scale 100 times 50, we can see that grid partition and TAZ partition achieve the same performance. However, again, if we're using scale-independent matrices, we can see the TAZ partition actually achieves much better performance, especially for the airport region. And last, we investigate individual units. So here we compare the units of our airport region and our highway station region using TAZ partition and grid partition again. We can see that with TAZ partition, the predictions for the airport region are significantly improved, whilst those for the station are not improved much. This is probably because the TAZ for the airport region is very big, so the traffic volume there is smooth. So from these studies, we can learn that fine-grained partition scales may not generate good scale-independent matrices, We can also see that root mean square error is not a good indicator, especially if we want to compare multi-scale partitions. Lastly, we can see that TAZ partition is more suitable than grid partition for deep traffic prediction. This also suggests that other partition methods, such as gradual partition proposed in GIS and transportation, can improve network prediction. Okay, so we should encourage collaboration in multiple disciplinaries. For the future work, we can try graph convolutional networks or attention mechanisms to improve the network prediction. Okay, so this is all for my talk. Thanks.
Okay, thank you very much. Very interesting presentation and really very complex and very old problem, and it definitely requires some new methods to solve it. And one of your key messages, as far as I understand, is that root mean square error is not a good indicator of error. But in fact, it's always a tricky question. What kind of errors you consider, absolute or relative? And RMSE is an attempt to somehow integrate absolute and relative prediction error. Do you have any idea of what kind of error indicator would be better for this kind of problems?
Okay, yeah, thanks. So actually, in our paper, we say like the root mean square error is not good for comparison over different scales. We didn't say it is not a good indicator. If you want to compare different scales, and we argue like it is not a good indicator.
Okay.
Okay, yeah.
But in this case, what could be a good indicator for comparing multiple scales?
Okay, so I see like in deep learning field, they're mostly using like three indicators, like root mean square error, like MAE, mean absolute error, and mean absolute percentage error. So I would say like from our work, maybe MAPE is the best one that can compare scales.
Okay, thank you very much. I'm afraid we have to go on to the next paper, and I'm really looking forward to seeing continuation of your work in the next year proceedings of IEEE visualization. Good luck. Good. So we move ahead to paper number 5, visual cause analytics for traffic congestion.
Hello everyone, I am Han-Byul at Zezheng University. This study is done together with Mingze P, Hae-Suk and Dr. Zheng. In this presentation, we are going to show visual cause analytics for traffic congestion. Urban traffic congestion has become an important issue. According to INREX's report, drivers in Boston waste 150 hours per year due to the traffic congestion. Previous studies have been focused on the traffic congestion prediction. However, it is not easy to find research that investigates the cause of traffic congestion. In this paper, we propose a novel technique to analyze the cause of traffic congestion. We detect vehicle flow change with the entropy and speed. Then, we extract the cumulative vehicle count curve and curve that quantifies the traffic flow. We classify the N curve into 4 congestion types using the CNN. Analyzing the causes of congestion requires considerable experience and knowledge. Therefore, we present a visual analytic system to analyze the cause of traffic congestion. The main contributions are listed as follows. We propose a technique to analyze the cause of traffic congestion. we present a technique to detect vehicle flow changes using the entropy and speed. We also propose a technique to classify traffic congestion types with CNN. As related studies, traffic monitoring, traffic pattern discovery, and traffic in situ exploration have been proposed earlier. We utilized GPS trajectory data in our work. The data have been collected from the taxis and buses in 3 different cities. The data contain the vehicle ID, time, and GPS coordinates. We apply GPS filtering technique to improve the data quality. According to the Federal Highway Administration, congestion types are classified into large traffic volume, bottleneck, traffic accident, bad weather, and poor signal time. According to the traffic flow theory, bottleneck, traffic accident, and bad weather have similar vehicle flow patterns. Therefore, we define 4 congestion types as presented here. For detecting vehicle flow changes, we analyze the vehicle speed and entropy. When calculating the degree of congestion, only the average speed have been considered at a particular time and location. Here, we show 3 different vehicle flow patterns. All vehicles are passing with an average speed of 20 km per hour. Therefore, it is not easy to differentiate the vehicle speed change only with the average speed. As a solution to this, we apply the entropy to classify the vehicle speed changes. The entropy is probability model expressing uncertainty or degree of disorder. We utilize Shannon's entropy as following. For the event probability Pxi, we divide the urban area into multiple tiles. We load the trajectory data contained in each tile. We create a histogram of the vehicle speed. Xi is the number of vehicles corresponding to the speed in each histogram bin. Therefore, Pxi is the probability that a certain speed interval is observed. After detecting the congestion area with the entropy and speed, we quantify the traffic flow using N-curve. The N-curve is a graph that represents the cumulative count of the departing vehicle and the arriving vehicle over time in the traffic flow theory. When the vehicles move from X1 to X2 at free flow conditions, N1 and N2 are the N-curve of the vehicle passing from X1 to X2. TTFF is the travel time with the free flow conditions. When traffic congestions occur between times T1 and T2, the N-curve of the vehicles passing through the location X1 appears as N1 as usual. However, the N-curve of the vehicles passing through the location X2 is changed to N'2. Therefore, the travel time is delayed changed from TTFF to TTFF plus TT delay. The number of vehicles under this traffic congestion type is Vn plus I minus Vn. And their total accumulated delay time is shown as Td. The N-curve is useful for understanding the traffic flow patterns in the congestion zones. Especially, the total delay time Td is critical to identify the congestion types. 4 congestion types have unique Td patterns as shown in B1 to B4. Moreover, each Td pattern has a unique vehicle flow pattern as shown in A1 to A5. We use the convolutional neural network to automatically classify the Td patterns into 4 congestion types. Our CNN model consists of 2 convolution layers, 2 pooling layers, and 2 fully connected layers as presented in A. Our CNN architectures perform better compared to AlexNet and ResNet as shown in B. Here, we introduce our visual analytics system. The visual analytics system supports 4 analytical procedures including parameter setting, identifying vehicle flow changes, detecting congestion routes, and analyzing causes of congestion. The first step in the traffic congestion analysis is to set initial parameters. We select a city, date, time, and several other conditions on the dashboard. The header filter allows us to analyze the traffic congestion patterns of moving vehicles only in a specific directions. When the city is selected, we define a tile on the city map. In this case, we divide the tile at intervals of 1 km by 1 km. The second step is to investigate vehicle flow changes. We use the parallel coordinate plot, scatter plot, and tile map. The PCP enables the analysis of the vehicle flow changes over time. The x-axis is time, and the y-axis is the vehicle flow entropy. Each line represents the entropy value over time in each tile. Our system supports a time series clustering in the parallel coordinate plot. Figure A shows the entropy change of all tiles in Beijing between 0 AM to 10 AM. We select the time in the PCP and brush the entropy range to see corresponding tiles on the map in B. We also clustered the tiles in the PCP by the k-mean clustering on the specific time. Figure D presents 3 clusters colored as magenta, cyan, and green. The magenta and cyan cluster with large vehicle flow changes are concentrated at the center of Beijing as shown in figure E. On the other hand, a green cluster with small vehicle flow changes can be observed outside Beijing. The scatter plot allows us to analyze the relationship between vehicle speed and entropy. The x and y axes of the scatter plot are normalized entropy and speed. Each point represents the tile. The tile map visualizes the tiles brushed in PCP and scatter plot. The tile map allows us to detect the congestion candidate zones. In the third analysis procedure, we detect road with the actual traffic congestion from the candidate zones where the congestion is suspected to occur. In this procedure, the system provides the map and glyphs. Before we introduce the map, we are going to briefly present the glyph. Figure A shows an example of our glyph at a four-way intersection. The glyph represents the 3 types of information, including traffic volume, average speed, and flow entropy. The glyph consists of a set of sub-glyphs that describes the inflow and outflow of vehicles as shown in B. The vehicle speed is encoded with the green to red color scale. The entropy is encoded in the purple to brown color scale, and volume is encoded in the bar height. Back to the visual analytics, we can estimate the road status based on the direction and volume of vehicles from the glyphs. We can also brush the road needed for the additional congestion cause analysis. In the first analysis, we analyze the causes of traffic congestion on the road. When we brush the congestion road on the map, the system provides the congestion type, N-curve, and calendar chart. The N-curve quantifies the vehicle flows, and the system shows the congestion type from the N-curve. The calendar chart provides the past congestion types for the road we have brushed. Therefore, we can examine the traffic congestion status and the congestion types using our visual analytics system. Now, we'll demonstrate the effectiveness of our visual analytics system with a case study. Here, the traffic accident affected the vehicle flow changes on the roads. Route 1 is merged to Route 2 at the intersection. In Figure A, the travel time suddenly increased on Route 1 from 6:30 AM on September 6. However, on August 30 in Figure C, there's no similar phenomenon found. This means that the traffic flow has changed due to external factors on September 6. Moreover, the traffic congestion on Route 2 on September 6 in B is lighter than one on August 30 in D. The CNN classifier the N-curve pattern on Route 1 as congestion type 2, but lack traffic accident, bad weather, and special events belonging to this type. In Figure A, Route 1 has a sudden increase in travel time. It indicates that external factors are likely to affect traffic congestion. In order to search for external factors, we monitor the traffic information. According to Seattle Police, a traffic accident occurred at the interchange of Route 1 entering Route 2. Therefore, we can deduce that the traffic accident caused a sudden increase in the travel time on Route 1. More case studies are found in the paper. In this paper, we introduced a visual analytic system to analyze the cause of traffic congestion. We used the entropy and speed to detect vehicle flow changes. We applied the N-curve to quantify vehicle flows. Also, we presented CNN to classify the N-curve. As a future work, we plan to develop advanced deep learning models to classify congestion types. We will also investigate on optimal dynamic traffic signal control at the city level. Thank you for watching my presentation. If you have any questions, please send us an email. Thank you.
Okay, thanks a lot for the presentation. The presenter asked to send emails to him with questions or post the questions in Discord. Therefore, we go ahead immediately to the next final paper of our session. Last but not least, Crime Analyzer, Understanding Crime Patterns in São Paulo. And I'm looking forward to this presentation.
Good morning, everyone. I'm going to talk about Crime Analyzer, understanding crime patterns in São Paulo. Studying crime patterns in big cities is a challenging problem because they typically present large spatial areas, great variability of patterns, and a high volume of crimes ranging from petty thefts to homicides. Moreover, the search for a high prevalence of crimes ends up neglecting sites where certain types of crimes are frequent but not sufficiently intense to be considered statistically significant. In our study, we addressed the challenges of analyzing criminality in São Paulo, the largest city in South America, located in Brazil, one of the largest countries in the world. So, in collaboration with a team of sociologists with a large experience in crime study, in this work, we focus on the analysis of criminal activities in São Paulo City. For that, with the help of the police department, we worked with a dataset from 2000 to 2006. The attributes of these datasets are the code of the census block, it is a neighborhood, the type of crime, and the date and time of the occurrence. We have 127 crime types, so we considered only the most 5 prevalent ones. And finally, this dataset was divided into 3 categories. With this dataset and 5 years, we have a lot of data. In addition, in São Paulo, there are more than 30,000 census blocks. Based on the challenges and analysis tasks described in the paper, as a first approach, we propose the Crime Analyzer. Crime Analyzer enables simple, intuitive visual resources to carry, filter, and visualize crime data. These visual resources are supported by mathematical and computation mechanisms and adapted in order to extract and represent the information. The models of our pipeline are the database to filter spatial, temporal, and crime type, the hotspot detection that is one of the main contributions, and 3 models to data visualization such as spatial, temporal, and hotspot visualizations. Specifically for hotspot identification, in this paper we adapted non-negative matrix factorization. NMF is widely used in other areas, for instance, image processing. I'm going to do a brief introduction to NMF. N by N matrix X is said non-negative if all entries X are greater or equal to 0. The goal of NMF is to decompose X as a product W, H, where W and H are non-negative with dimensions n by k and k by n respectively. In mathematical terms, NMF is defined as a minimization of this function. So, visually, X is defined as the multiplication of W and H, where W is considered the base, the information columns, and H the coefficients. Each column of X could be represented as a linear combination of columns of other matrices. Let's see an example of a region with 25 sites. We simulated the criminality of 5 years. So, for 25 census blocks and 5 years with month discretization, the modeling would be in a matrix of 25 by 60. Well, we have our matrix X. The value in each cell corresponds to how many crimes a census block has in a month. In order to simulate many situations, each site has a particular crime behavior. For instance, for site A and B, we simulated sites with high criminality rate. For site C, we modeled a site where it is not high, but it is very frequent. Finally, for site D, we modeled a site where the criminality is low, but there is some month with really high criminality. So, this is our region with 25 sites labeled A, B, C, and D. We have our matrix X, and we applied NMF matrix decomposition to gain the matrix WH. Doing the decomposition for K equal 3, it could be noticed that the color in the original matrix represents the number of crimes. Those that are blue are 0 or close to 0. In this figure, it could be noticed the high criminality of the sites A and B. In C, the criminality is not high, but it is frequent. And finally, in D, there is huge criminality in some time slices, using an NMF decomposition with rank K equal 3. Notice that the entries in the first leftmost column of W have values close to 0 almost everywhere, except in the entries corresponding to the sites A and B. Therefore, the hotspot derived from the first column of W highlights sites A and B as the relevant ones. The high prevalence of crimes on those regions can clearly be seen from the first top row of matrix H, which has most of its entries with non-zero values. The second column of W is mostly null, except in the entry corresponding to site D, where crimes are not frequent but happen with high intensity in particular time slices. Notice that the second row of H has basically 2 entries different from 0, corresponding exactly to the time slice 35 and 47, where the site D faces a large number of crimes. Finally, the last column of W gives rise to a hotspot that highlights site C, where crimes are frequent, but in smaller magnitude when compared to A and D. The incidence and intensity of crimes in C are clearly seen in the 30 bottom row of H. We applied other experiments with different values of k. More details of these experiments are described in the document. Thus, we developed Crime Analyzer, a visualization-assisted tool that integrates the analytical machinery in a set of linked views. Crime Analyzer operates on target spatial regions to uncover relevant information of the region as a whole, and also from its individual sites. This is an overview of our system. The first of these is Map View, which allows the user to choose the region to study, and within that region, there are census blocks or sites. The second is Hotspot View, which is basically a hotspot representations in small multiples. Cumulative Temporal View, which shows the behavior of the crimes taking into account some temporal labels. For example, how is the behavior of crime in the month, days of the week, and period of the day. Global Temporal View, temporal evolution of crime activity along the years. Filter Widget is a menu to filter the crime types and the years of study. Ranking Temporal View that basically shows the evolution of the types of crimes over the years, besides making a comparative between the types of crimes. Radial Type View shows the evolution of the crime, considering the crime types, its complement to Rank Temporal View. A set of case studies revealing interesting phenomena about the dynamics of crime in São Paulo, supporting hypotheses and theories raised by domain experts and described in the literature. For instance, the goal of this case study is to analyze patterns of crimes in different regions of the city, in order to understand how they change according to urban characteristics. To perform the study, we selected 4 areas in São Paulo, 2 in the center of the city, denoted as C1 and C2, and 2 in residential areas pointed as R1 and R2. Both C1 and C2 have a huge flow of people during the whole year. Residential areas R1 and R2 differ in terms of the economic level of residents. R1 is a middle-class neighborhood, while R2 is a richer area with luxurious buildings and houses. Using the visual components of Crime Analyzer, we could analyze the behavior of the regions. For C1, the ranking type view shows how the incidence of the 5 most frequent crimes varies along the time. 2 crime types lead to the ranking along the years, the beige and the pinkish curves on top, passerby robbery and auto burglary. Inspecting other sites by simple clicking on them on the map view, we concluded that passerby robbery and auto burglary are the prevalent crime types in almost all sites in C1. Performing the same analysis for C2, the ranking type view shows that there is one crime type that has been grown over the years, green curve cargo theft. Crime Analyzer reveals that cargo theft is not prevalent in the whole region, but it is concentrated in just a few sites, being the dark brown site in the center of the region. Notice that cargo theft became the 3rd most common crime type in that region over time, behind only of passerby robbery and document theft. Moving from the city center to more residential areas, the analysis reveals a substantial change in crime patterns. In the residential region R1, for example, passerby robbery remains the most common crime type, followed by document theft. However, some sites in R1 have bus robbery as the 2nd most common criminal activity. The importance of bus robbery in R1 is easily noticed in the ranking type view, where the blue curve bus robbery reached high rank levels in several opportunities. Similar to what happens in C1, C2, and R1, region R2 does have passerby robbery as the predominant crime type, which can clearly be seen from the ranking type view. Moreover, home burglary is the most relevant crime in one of those regions. In fact, home burglary is a relevant crime in R2 as a whole, as indicated by a reddish curve in the ranking type view. Notice that home burglary has increased in importance over the years. The discussion above shows that the visual analytic functionalities implemented in Crime Analyzer are able to sort out analytical tasks described in the paper in a simple, intuitive, and effective way. The second case study has been driven by domain experts, and they were interested in a particular type of crime, cargo theft. Although cargo theft does not figure among the most prominent crime types in São Paulo, domain experts focused their analysis in 2 important highways, SP-230, which connects São Paulo to states in south of Brazil, and BR-116, which connects São Paulo to Rio de Janeiro. In order to perform their analysis, domain experts relied on the polyline selection tool to select a considerable number of sites along the highway and avenues that connect the city to the highways. The ranking type view reveals the crime patterns in each hotspot. Notice that in BR 116, cargo theft figures among the most relevant crimes, becoming the second most relevant crime at multiple times. In SP 230, though, cargo theft is not predominant, not appearing among the 5 most relevant crimes in the ranking type view in any hotspot. To center the analysis in cargo theft type, it is possible to filter to select that type, filtering the data such as hotspots, and all the views are updated to depict only information related to the selected crime type. After the hotspot calculation, the crime analyzer viewing tools also makes clear that in BR 116, cargo theft takes place mainly along the highway, while in SP 230, the relevant sites of each hotspot are located in the avenue that connects the highway to the city. Domain experts consider this an important finding because it is known that the modus operandi of criminal offenders, and hence the location of cargo theft, change according to the transported product. So, the possibility of identifying these roads should make public security policies more efficient. Another interesting aspect pointed out by the experts is the capability of revealing hotspots associated with sparse criminal activities, as the one depicted in Crime Analyzer. Notice that these findings could hardly be made without the visual research enabled by systems such as Crime Analyzer. Finally, conclusions. In this paper, we presented Crime Analyzer, a visual analytics tool to support the analysis of crimes in local regions. It has been developed in close collaboration with domain experts. We propose a new hotspot detection technique based on NMF. Our proposal was validated by comparisons, experts' feedback, and case studies with real data. And as part of case studies, we validated seasonality and near-repeat victimization in São Paulo City.
Hello. Thank you very much for your presentation. Very interesting project, and I think this is a really very important problem, and I hope that your work will help to improve the fighting against criminals in São Paulo. And one of the questions that you got in YouTube is you actually use data from quite long ago, and the audience is interested if your work had some impact on fighting with crime. Did it make it more efficient or not yet?
Actually, we are working in different projects for Sao Paulo City, and we are working directly with Center of Study of the Violence. So hopefully our results will help to reduce the criminality in Sao Paulo. And we are trying to validate different hypotheses to reduce the criminality in Sao Paulo City.
So you have different kinds of stakeholders involved in working with your system. Because another question that was asked in Discord is for whom this system is targeted for. But I think people need to look in your paper that describes your audience. I also have one question. You look at absolute counts of different crimes in regions, but maybe it would make sense to somehow normalize these crime counts by registered population or by daytime population or by traffic or other relevant attributes. Did you consider this idea?
Actually in our future work we are considering different factors such as socioeconomic factors, social factors such as the population, and also the infrastructure.
Okay, thank you very much. I think it's time to close our session because in less than half an hour, we will have a new round of several parallel sessions. Thank you very much to everybody for presenting your work and answering questions, and thanks to the audience for questions. Goodbye.
To interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
Traditional clustering tools do not include users in the analysis loop. We present PK clustering, a new approach for interactive clustering using VIS. First, users specify their prior knowledge. Several algorithms are run and match with the prior knowledge. Users then build a consolidated clustering iteratively with suggestions based on consensus, the graph, and their knowledge of the data. The result is a consolidated clustering.
Do you have a research question but aren't sure how to go about answering it? Are you interested in collaborating with psychologists but want to learn more about how they do research? Our paper presents a comprehensive toolkit of empirical methods organized across 4 categories to help you think about presenting visualizations as experimental stimuli in order to explore and measure how people perceive data. Check out our paper.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
We present columnar data augmentation through visual analytics. Kava lets users augment their data with additional attributes found on knowledge graphs. To construct a new attribute, each row of a dataset is mapped to a node on a knowledge graph. Each augmented datum is the result of a query over the knowledge graph in the neighborhood of that node.